Where does time begin? Where does it end? Does time have an end? Was there time before the Big Bang? Just as everything has a lifespan, so too does our solar system. When our solar system reaches the end of its life, will time still exist? Is time something that flows independently of everything else, a straight, unbroken line? According to figures like Newton and Galileo, the great masters of classical physics, time is absolute, unchanging, fixed, and flows independently of everything. Newton is the name most synonymous with time in the public mind. One day, a young man working at a patent office in the city of Bern wrote something in his notebook. Newton, I am very sorry. With these words, he was challenging Newton, Descartes, Galileo, and dozens of other scientists, the names that had shaped history. Albert Einstein was essentially telling some of the most celebrated scientists who ever lived that they had gotten it wrong. This was the same man who, as a student, had once said, "This fact or that fact doesn't interest me. I want to learn how God thinks. Everything else is just detail." And what else could you expect from a man who, even in the hour before his death, picked up his notebook and pen in an attempt to take the final step towards solving the mind of God, still working on his theory of everything? Truly understanding science is impossible without first understanding Albert Einstein. But today's subject is time, and Einstein has something to tell us. To understand time, we need to look back in time, to where it all began. We won't go as far back as the Big Bang or the philosophers of antiquity. We can discuss those separately if needed. But we do need to take a look at the 16th century, when the phenomenon of time was first studied from a scientific perspective. What a remarkable century it was. The 16th century produced an extraordinary number of brilliant scientists, didn't it? Galileo, Newton, Barrow, Descartes. It was a century that stretched into the 17th century, an era some have called the Age of Enlightenment. The first man to work scientifically on time was Galileo Galilei. The concept of time that would be accepted for centuries then took nearly its final form with Isaac Barrow and Isaac Newton. According to these scientists, as we mentioned, time is absolute, unchanging, and fixed. That is the very essence of what we mean by Newtonian time. And this definition of time, accepted as constant, was a phenomenon that moved at a fixed rate at every point in the universe, identical for everyone, measurable yet imperceptible, beyond sensation. Newton believed that time and space were two entirely separate entities. He had convinced himself that time would continue to exist even if everything in the universe ceased to be. As Shakespeare's famous line goes, all the world's a stage, and in Newton's view, the one unchanging backdrop on that stage was time. Time was the one constant he never altered in any of his laws, and therein lay a problem, one Newton was never able to solve in his lifetime. A problem he believed was the work of God, something beyond our perception. The most telling evidence of this was hidden in the movements and orbit of Mercury, the innermost planet in our solar system. Newton's laws could calculate everything, the motion of a falling apple, the movement of ships, even the precise orbit of the Earth. Yet Mercury stubbornly refused to conform to these calculations. There was always an irregularity in its orbit, something that simply would not fit the equations. It must be the work of God, Newton said at this point. Some scientists attributed Mercury's anomalous movements to another object, a planet we could not see, because that was the only way they could explain them. Yet it didn't feel right. They could not reconcile Mercury with any science-based formula. And as long as time was considered constant, they never would. Now I'm going to ask something of you. I know it's difficult, but I want you to forget everything you know about time. Forget how time progresses, how it flows in a straight line, how we live and die along that line. Forget all of it. Forget it because we need to completely dismantle that perception. Because it is wrong. Who says so? No, the person you're thinking of is coming in a moment. First, it was Wilhelm Leibniz who introduced this idea. For Leibniz, there were events that came before, after, or simultaneously with one another. Time simply helped us sort and categorize those events. Then Immanuel Kant joined the effort to re-examine time. Kant argued that time was not something that existed on its own, nor was it a sequence of relationships among independently existing things. In other words, it didn't merely file events away. According to Kant, time was simply the way our minds organized the experiences we had. He proposed that things existing independently of our minds, things beyond our perception, were not in fact situated in time at all. How could something we do not perceive exist within our time? Could this be considered the first attempt at a theory of multiple realities? And then, the man we had been waiting for. Albert Einstein would put the final period on all these debates. In 1905, he widely regarded as the most brilliant year in both physics and Einstein's own career. Albert Einstein published 4 groundbreaking papers, one of which was the special theory of relativity. A decade later, after an intense period of focused work, he published the general theory of relativity, cementing his name in golden letters in the history of science. What is time? This was the question that occupied Einstein's mind most deeply, even as someone who greatly admired Newton. Because after examining the equations in Maxwell's work, Einstein's thinking had fully crystallized. The one constant in the universe was the speed of light. The only thing entirely independent of us, indifferent to our direction or position, was the speed of light. And if that was true, then everything we had learned needed to change, especially Newton's laws, because time could not be constant. Let's work through an example. Imagine a scenario in which the sun suddenly ceases to exist. Under Newton's law of gravity, the Earth would instantaneously break free from its orbit and begin drifting into the void of space. And this would happen immediately. This is because, under Newton's law of gravitation, you can think of the gravitational force between two objects as a rope, a fixed instantaneous connection. But according to Einstein, no such event could occur, because the one constant in the universe is the speed of light, and nothing can exceed it. The speed of light is our absolute limit. It takes approximately 8 minutes for sunlight to reach us. And since gravitational force also travels at exactly the speed of light, if the sun were to vanish right now, we could continue for 8 full minutes without noticing a thing. This theory became one of the most significant in the history of science. Here is something that strikes me as remarkable. Albert Einstein might never have discovered this, and we could have gone on living under Newton's laws without ever realizing the difference. Because Newton's laws don't produce errors we can detect in daily life, they work correctly about 99% of the time. But that 1% that causes no trouble for the rest of us was a problem for minds like Einstein's, and in his view, everything deserved an explanation. How did Einstein arrive at this conclusion? In truth, Einstein had sensed it at the age of 16. In one of his famous thought experiments, there was a train and 2 people, one inside the train and one outside watching it passes. The train was moving at an extremely high speed. Now imagine that behind this train, at intervals of 100 meters, there are 2 trees, and at the exact same moment, lightning strikes both trees. According to Einstein, for the person standing outside the train, both strikes happen simultaneously. But from the perspective of the person riding the high-speed train, the lightning strikes the first tree first, and then, a moment later, the second. The same event, yet 2 different moments in time. How is that possible? Let's try to make sense of the constancy of the speed of light with another example. Picture 2 cars driving side by side, each at 60 kilometers per hour. For the passengers in each car, the other car appears to be stationary, not moving at all. But if one car accelerates to 80 kilometers per hour, then from the perspective of the car doing 60, the faster car appears to be moving at 20 kilometers per hour. That is our everyday intuition about speed. But this logic breaks down completely at the speed of light. The speed of light is precisely 299,792,458 meters per second. For the sake of simplicity, let's call it 300 million meters per second. Now imagine we build a rocket traveling at 200 million meters per second, and we travel alongside a photon, a particle of light. Under normal logic, if we measure the speed of that photon from our rocket, the result should be 100 million meters per second, right? But it doesn't work that way. No matter where or how you measure it, the speed of light will always be exactly 299,792,458 meters per second. E equals mc squared, the most famous equation in physics. Here, E represents energy, m represents mass, and c squared is the speed of light squared. When Einstein first wrote this equation, he expressed it as m equals E over c squared, meaning energy and mass are interchangeable. In other words, energy and mass are fundamentally the same thing. Everything you see and know is at its core energy. You, me, everything, all composed of energy. And we are talking about an enormous amount of energy. Consider a needle. If we could convert every atom that makes up that needle into pure energy, it would release the equivalent of 18 kilotons of TNT, a force approaching the power of an atomic bomb. This equation, and by extension Einstein himself, tells us the following. As the speed of an object increases, so do its energy and mass. As it approaches the speed of light, it requires infinite energy and therefore infinite mass to maintain that speed. This is precisely why exceeding the speed of light is impossible. What challenges us further is this. According to the physics we perceive, speed multiplied by time equals distance. But when you plug the speed of light into that equation, the laws of physics as we know them break down. Because the speed of light is constant. Therefore, something between distance and time has to give. This theory about the speed of light was confirmed in real life in 1971. In an experiment known as the Hayfel-Keating experiment, 3 atomic clocks were synchronized with one another, and 2 of them were placed on aircraft flying in opposite directions. The third remained at the airport. When the aircraft landed, the clocks were no longer in sync. The atomic clock on the eastbound aircraft was 59 nanoseconds, billionths of a second, behind the one that had stayed at the airport. The westbound clock was 273 nanoseconds ahead. Hard to grasp, isn't it? People generally struggle to accept this. But even a single example from everyday life is enough to appreciate the importance of this theory. GPS systems, for instance, because satellites in orbit are moving at very high speeds, a small time difference accumulates, and this difference must be continuously corrected and synchronized. Without this correction, the location shown by apps like Google Maps could be off by kilometers, and we would be unable to pinpoint anything with accuracy. That is it. Today we attempted a brief analysis of the general theory of relativity, which Albert Einstein committed to paper in 1905. Even when these concepts seem difficult to grasp, they are all subjects that directly affect our lives. People sometimes say, this doesn't concern me, but there are always points where these ideas touch every one of us. I believe that thinking about yourself and the universe is life's way of asking you, understand why you are here. It is truly remarkable to appreciate how much people like Albert Einstein and the other figures in this video have helped us perceive life and the cosmos. We are just getting started on this channel. We'll be exploring many different topics and scientists along the way. In our next video, let's see where we find ourselves, who we'll be with, and what we'll be uncovering.
In this video, we will push the limits of our body, and while doing so, we will of course touch on the most extreme points science has taken us to. Everyone knows what G-force is. No, I'm not talking about the graphics card. What is G-force? Let me explain it this way. You know that feeling when you are driving very fast in a car and you feel like you have gotten very heavy and are being pressed into your seat? Or when you are on a roller coaster and feel like your organs are about to come out? Well, that is G-force. Scientifically, G-force, that is gravitational force, is the force that keeps us on the surface of the Earth, and it equals 1g. We do not feel this. It is the most basic G-force, and compared to the examples we're about to give, calling this a force is a little ironic, because essentially, with every increase of 1g, a load equivalent to your body weight multiplied by that force is placed on your body. Let me explain with a simple example. Say you weigh 80 kilograms, but that weight is your value at 1g. If we were to put you in an environment of 10g, your body would feel as though it were carrying not 80 kilograms, but 800 kilograms. If everything is clear, let's start with examples of g-forces from low to high. First, 0g. Astronauts who go to space can experience these, since they have left Earth. They can move as if they have no body weight at all. In fact, some astronauts have been observed to have great difficulty standing and walking when they return to Earth. Another effect of 0g is height increase. Yes, you heard that right, because some astronauts returning from space are not exposed to the effects of gravity, the disk spaces in their spines increase, and a height gain of a few millimeters has been observed. Of course, we are not talking about a permanent height increase. When they return to Earth, they are exposed to gravitational force again, so their height returns to what it was. Just imagine if it were permanent. Everyone who wanted to grow taller would be racing to become an astronaut. Anyway, let's not stray from the topic. We said 0g, we already live and know 1g. Now, as we said at the beginning of the video, it is time to push the limits of our body. F1 drivers, whom many people enjoy watching and some admire, are exposed to approximately 5g on a sharp corner. They feel a force equal to exactly 5 times their body weight. This proves just how demanding a sport they compete in and how physically robust they actually are, doesn't it? Before continuing with our examples, let's briefly look at how g-force is calculated. In short, g-force equals maximum speed divided by the time taken to reach that speed. And if we then divide that result by 9.81 meters per second squared, we find the g-force. The 9.81 here is the gravitational constant discovered by Newton. This constant tells us something very important and has greatly simplified our work in scientific developments. The meaning of the constant is this. If you drop any object from a height, it will travel 9.81 meters per second toward the Earth's core. Of course, in this equation, we are ignoring factors such as friction and air resistance. A ship and a balloon dropped from the same height will hit the ground at the same time. Now, let's calculate the g-force of a sports car together. A car with a maximum speed of 200 km per hour corresponds to 56 meters per second. Let's assume it reaches that speed in 4.6 seconds. In that case, the g-force applied to us, traveling inside the car, is 56 divided by 4.6 equals 12 meters per second squared. And dividing that by 9.81 gives us 1.2g. In other words, the force pressing you into that seat is only 0.2 more than the normal 1g. Actually, 0.2 may sound like very little, and it is not that little. It just seems small compared to the other examples in our video. So let's continue. We calculated how much you feel in your sports car, 1.2g. So how much g-force do you think the astronauts, who we just said experience 0g in space, feel inside the rocket during launch? Exactly 3 g's. From this point on, if you multiply each g-force value I give by your own weight, you can better understand how much greater a force they are experiencing. Let's gradually increase a little more. For example, the drivers inside specially built vehicles called top-fuel dragsters are exposed to approximately 4.5 g. It is a little difficult for us to get our hands on those vehicles, but we can also be exposed to high g-forces. The roller coasters I mentioned at the beginning of the video, which make you feel like your organs are coming out, can give us that experience. On advanced, latest generation roller coasters, especially in sharp, sudden turns, our body is exposed to 6 Gs. In other words, if you weigh 80 kilograms, you feel like you weigh 480 kilograms. Being exposed to this G-force for a long time can cause injuries and loss of consciousness. That is why it is worth being careful when getting on roller coasters.
Now let's get to the point of truly pushing the limits of the human body. When it comes to G-force, the names that come to mind as the greatest experts are fighter pilots. Fighter pilots resist a force of approximately 12 G during takeoff, dives, and sudden maneuvers. That is why not everyone in the world succeeds in this training. In their training, pilots are spun in machines called centrifuges, just like a washing machine. Centrifuge machines automatically calculate how much g-force the person inside will feel and rotate at the required speeds to simulate g-force in a laboratory setting. During training and while flying aircraft, pilots sometimes experience an event called GLOC. GLOC is when the blood in our body is pulled downward and the brain and organs are momentarily deprived of oxygen. When a person is in this state, they momentarily lose consciousness and enter a kind of semi-sleep state. However, as blood flow returns to normal, the person can regain consciousness. Next is the event involving Eli beading, the highest G-force a human being is known to have been exposed to. During the Cold War, this fighter pilot voluntarily agreed to ride a device called a rocket sled as part of some experiments that were far too dangerous to test in manned fighter jets. He was exposed to exactly 82.6 G for just 0.04 seconds. Normally, as you would understand, this level of G-force is enough to kill a person. But because the exposure lasted such a short time, Eli beading survived. However, even being exposed to that force for just 0.04 seconds caused damage to many of his blood vessels and resulted in internal bleeding. This was a controlled test. It could also be called a laboratory experiment, but unfortunately, many people around the world are exposed to even more than this every day involuntarily. Where? Sadly, in traffic accidents. If a high-speed vehicle hits a stationary wall or object, the occupants are exposed to a greater G-force than Eli beading experienced. This is why we must follow traffic rules to the very end. During a race, Kenny Bragg's brakes locked up while going at full speed, and he experienced exactly 214 grams at that moment. He felt as though his body weight was exactly 214 times greater than normal, which corresponds to approximately 14.5 to 15 tons. Under normal circumstances, we would naturally assume that someone feeling such a weight would have little chance of survival. Yet Kenny survived despite every bone in his body being broken. Let's raise the G-forces a little higher. The next example, can you guess? It comes from a machine that all of us are familiar with and that I think every one of us has used at least once. The washing machines I just mentioned above can actually be called the centrifuge machines in our homes. Especially during the spin cycle, these machines rotate with a force exceeding 400 G. And now, let's step outside our world in keeping with the style of our channel. The magnificent power of the universe is before us once again. Let's look at neutron stars. These stars are formed when the material left over from supernova explosions collapses inward under the effect of gravity. Although their mass is very large, their volume is extremely small. For example, some neutron stars are only 10 to 15 kilometers in diameter. In such a case, their density and consequently their gravitational pull are enormous. The gravitational force, that is, the G-force, of a neutron star is approximately, hold on tight, exactly 7 trillion G. Do you know what that means? It is known that there are approximately 2,000 neutron stars in our galaxy. And if we could reach one of them and somehow build a bridge made entirely of steel or iron, that bridge would disappear within seconds. And you could put what remains of that massive structure in your back pocket and go home.
And finally, fittingly for the last example, let's talk about the greatest G-force in the universe. This G-force is called Planck acceleration, or Planck time. This concept was discovered by Max Planck, and what he discovered refers to the shortest measurable slice of time. We explained how G-force is calculated. It is found by dividing an object's speed by the time taken to reach that speed. We agreed on that. Something else we need to remember is the speed of light, which we mentioned in our previous videos, the highest attainable speed. That is also settled. Well, Planck combines exactly these two things. He performs the calculation by calling the shortest time in which the speed of light can be reached the Planck time. And the resulting number, as you might imagine, is very, very large. This G-force, written as 68 followed by 49 zeros,
is thought to be what the universe was exposed to once. This G-force is accepted as the one that occurred during the Big Bang that formed the universe. It is also believed that forces close to this exist in black holes, but scientifically, we are not yet at the level to calculate this. One step beyond black holes, quantum physics begins, but that is the subject of another video. That's it. Today we push the limits of the G-force we are exposed to every day and try to elaborate on this topic and broaden our horizons. See you in another video.
In this video, we will take a journey into our past. When we say our past, what comes to mind? Which past can we even talk about? An hour ago? A day ago? Or a year ago? So is it simply the fact that these things happen in the past that makes them the past? Or is it our remembering them? If we didn't remember them, would those moments still count as the past? Today we're going to dig into exactly this question. Memories are a miracle that allows us to remember events that happened in the past. We could compare these to folders on a computer. Thanks to memories, our brain forms a connection between itself and reality and stores what is important to us. Unfortunately, there is a problem with memories. Memories are almost like a statue. Just as statues erode, corrode, and change over time due to the effects of nature, memories also change over time as other memories accumulate. There is a difference between how we remember yesterday and how we remember a year ago. This is a bit frightening because memories are one of the biggest parts that make up our personality. While memories prepare us for today, they also affect the decisions we will make in the future. So what does this changing of memories tell us? Actually, the bigger question is, how is a memory stored in our brain? Our brain is quite complex. We'll address this topic separately another time. But for now, we need to make the subject easier to understand. Although the models that simulate our brain have taught and told us a great deal, they still don't come close to a real human brain. These simulations that have been made can't really go beyond imitating the basic parts of our brain. Our brain is a machine that gives us abilities like thinking, feeling, judging, and deciding through the operation of roughly 86 billion neurons. Our brain sends and receives signals across the gaps between cells through incredibly complex synapses, using electrochemical root systems. This is how the 86 billion neurons talk. This conversation continues without interruption. A single neuron is connected to roughly 10,000 other neurons. When you consider all these connections together, the total number of connections reaches hundreds of trillions. This is far more than the number of galaxies we know of in our universe. Our existence, as a kind of miracle of these connections, is what gives us our personality. Of course, within all this complexity, some connections had to be weak and some had to be strong. This strengthening happens between two neurons that are triggered at the same time. We could call these a kind of friendship between neurons that like the same things. In this way, by calling in their other friends, meaning by triggering other strong connections as well, they strengthen those connections too. If we step back and look at everything I've described so far, there are billions of neurons, and each processes a tiny part of the incoming external input, forming separate clusters by strengthening their connections with other neurons triggered by that same input. Touch, sight, sound, taste, and feeling. Each of these senses has its own separate region in our brain. In other words, they form separate clusters. We could call these clusters the gears of the machine. They form your personality, that is, your hardware components. Every sensation you receive from the outside, sight, hearing, and so on, triggers these neurons and sets the gears in motion. As with any machine, a gear moving doesn't mean the whole robot is walking. The movement of the gears needs to be connected and consistent in an orderly way. Even as you watch this video, all your regions, eyes, ears, language centers, work in motion to process and analyze the video into your brain. and every bit of processing is etched into the depth of your brain. While watching a video, if the eyes and ears matter most, the brain prioritizes them and pushes other regions into the background. It's like a giant factory producing in harmony without everything getting mixed up, all working at full capacity at the same time. This is exactly what makes us feel human, the neurons in our brain working together in this harmony. To repeat, right now, all the regions of our brain necessary to understand this video are working. But these activities within this complex structure lose their effect and fade away over time, like a sound wave, meaning they have no lasting substance of their own. If we didn't have a memory mechanism, we would be permanently locked into the moment we're living in. We would have neither a past nor a future. So how does our wonderfully designed brain decide what is important? How does it understand what it should erase and what it should keep? If you have a thought on this, share it in the comments now. If you've written your comments, let's continue. There is a battle happening in our brain at every single moment. All the clusters I just mentioned are fighting with one another. Every input coming from the outside world and from our inner world adds new clusters to this battle. And these battles have a winner at every moment. The brain declares whichever cluster is strongest as the winner and decides that piece of data or that cluster is more important. As you watch this video, your brain, deeming the watching of this video important right now, has watched the video and formed the memory. Two things happen in your brain as you watch the video. First, the connections in the winning cluster become stronger and get stored in the memory center, that is, the hippocampus. Let's not go too deep into the hippocampus because it's very complex. For now, it's enough to know this. We've created a kind of preview file in our hippocampus, and we continuously record the configuration of the strengthening cluster into this file. And we file all the events connected to this cluster here, in sequence. For example, from now on, every time you watch a video from this channel, by matching the events happening around you with this video, a memory of ours will form, and it will be automatically recorded and its connections strengthened, forming our memory. How complicated and hard to understand this sounds, doesn't it? But we do all of this automatically, without ever being aware of it. Our brain really is an amazing organ. We've learned that our brain has many regions, and that within these regions there are millions of interconnected clusters. So, how do we remember memories? Any trigger related to a cluster in our brain causes that cluster to become active again and to become important to the brain once more. Because this activity had fallen into the background of the brain, reactivating it is very delicate and not always clear. Your hippocampus had kept a draft, but that memory remained far in the background and weak because no repetitions were done on it to strengthen it. This is exactly why you only remember memories that have truly strong connections and that affect you, because the connections of those experiences are strong. This is why you don't remember the taste of the cake you ate 2 years ago. But if you started a new job around that same time, you may have told the story of that day to your family or friends over and over, which strengthened the connections and turned it into an unforgettable memory for you. What I want to convey here is, you don't forget things related to you personally, but you forget the daily events you see in the news very quickly, no matter how big they were, because your brain never formed the relationship between you and that news story, and it wasn't repeated enough. There are a few ways memories avoid being forgotten. I just mentioned one of them. Another way is stepping outside of routine. For example, a song you listen to every day while walking the same route, on the same sidewalk, at the same pace, forms a very weak bond, whereas the very same song playing in your ears during a traffic accident you witness on that same route turns into a far more permanent, hard-to-forget memory. Emotions are truly powerful structures that carry very deep meaning and that have shaped and guided us from our ancestors down to today. Emotions motivate us to eat, to reproduce, and to make decisions in moments of danger. There are emotions that make us feel good, just as there are emotions that make us feel bad. When you feel a powerful emotion that has evolved over millions of years, your brain immediately acts in a primitive way, deciding that whatever is felt is necessary for survival, without weighing whether it is good or bad for you. This is why permanent, powerful memories are also made up of powerful emotions. The embarrassment from something you did in front of your crush, the stress of your first speech in front of a crowd, the emotion of having your first child, the feeling of losing your pet, the joy of beating your older brother at chess. If any of these examples I've listed stirred something inside you as well, it's now harder for you to forget this video too. This is a bit of a trick, but you can also help grow this chain of memory by sharing the video with your friends. By repeating those powerful emotions, we've now thoroughly strengthened the connections, and we've also grown our cluster by adding a new memory, a new connection alongside it. It's like tying a knot in a rope over and over. The strongest point is the one repeated the most, but it's also, at the same time, the most damaged point. How ironic. It gets stronger, we don't forget it, but the rope is no longer in its original state. It has changed, now with new centers of strength and new priorities. This is exactly how memories shape our personality. Sleep is also very important in solidifying the connections in our brain. During sleep, your hippocampus repeats the cluster your brain has selected as important, making it more permanent. As I said, this process only happens during sleep. If you don't sleep, you forget what you've experienced. This information could save your life while preparing for an exam or an interview, because if you don't sleep, you forget everything. And now that we've taken care of sleep too, congratulations! You now have an unforgettable memory. Really? Is that so? Some philosophers say that humanity's greatest ability is forgetting. Just imagine never forgetting a single thing that happened in your life. Not just the good events, but the bad ones too, never forgotten. A person could go mad. Personally, I wouldn't want to have such an ability. Let's go back to our topic. We were saying we had formed a permanent memory. Is a truly indelible, unforgettable memory even possible? To remember something, we theoretically need to have forgotten it. But to remember a memory, we need a cue. Anything that reminds us of that moment. A sound, a smell, maybe an item of clothing or a car horn. The library in our brain, that is, our hippocampus, begins scanning for that cue and activates the matching cluster. After the trigger, fragments of the memory are gradually brought back. A pattern begins to emerge, and then memory appears before your eyes. This is how the sequence unfolds, but with a small difference. The clarity of the image that appears before your eyes depends on the strength of the connections in your cluster. This is not like watching a video. As you experience the memory in your mind, the weak bonds melt and become moldable again. The memory was stored with the mood you were in on the day it happened, but your current mood is very different. Maybe you were angry and tired when you experienced the memory, but right now you are very cheerful and energetic. And this current mood begins to seep into your memory, reshaping the weak bonds. Maybe you felt sad while living through the memory, but now this memory is very funny to you. You don't do this on purpose. Your brain simply reprocesses your memory according to your current mood. And once your memory is finished being recalled, this is now your new reality. Your memory has changed according to your mood and has become solidified again. This is why things that upset us greatly at the time become less painful for us as time passes, and sometimes even turn into memories we laugh about. Every time we bring back a memory, our brain reshapes it by making new additions and removals. In other words, it adapts our past to our present. Sometimes it takes this reshaping too far, merging it with other memories, discarding parts it deems unnecessary, and adding elements from other memories. This shows that our memories are integrated into our own learning system. As new memories come in, old memories get updated. And every time we remember an old memory again, it is no longer that same other memories. Looked at this way, the more times we're remembering the same memory, the further we drift from the experience at the moment it first formed. So the next time you're telling a story and say, I'm sure this is exactly how it happened, think twice. We can't notice this process because it's spread out over time. This is why the memories you experience today are what your present self feels. As I mentioned above, no memory above exactly the same twice. Your future self will be shaped by looking at today's memories, but they won't feel the way you feel now. That's it. Today I try to talk with you about the metrics that make us your are. We've seen that a person, if this way is doing, could even convince themselves of an altered memory from the start without experting it. From now on, whenever you find yourself in a difficult society for any reason, let this come to mind and remember to tell yourself, I can even change my own history. I can dance this too. See you in the next video.
In this video, we will witness the incomprehensible size of the universe. By the time the video ends, we will either lose ourselves or discover new selves within our own inner world. If you are ready, let's begin. Our universe, born 13 billion years ago, is approximately 46 billion light years in diameter. So what does a diameter in light years mean? This diameter is connected to the rate at which the universe is expanding. It has now been proven that the universe continues to expand. In other words, the speed of light, which is the limit for us humans, is not a constraint for the universe. 46 billion light years sounds truly enormous. If you told someone the universe is 46 billion light years in diameter, they would probably say, yes, that sounds big. But what does this number actually correspond to in concrete terms? In this video, we will try to make this number, the size of the universe, tangible and illustrate it in a way that our small brains can understand. Let's get started. Our starting point is, of course, our own Earth. Why? Because it is easier for us to grasp. When we look at the universe, Earth may seem small to us, but it is not actually that small. Driving a car at 100 kilometers per hour, it would take 17 days just to complete one lap around it. Or if you have a plane, you could do one lap in about 3 days. And we have been living on this large planet for hundreds of thousands of years and will continue to do so. And we have still not fully explored this world. Now it is time for our nearest companion, the moon. The moon feels so close that it seems like we could reach out and touch it. For most of us, the moon was our first encounter with space. That is how close it feels. Yet our small companion, which seems so near to us, is exactly 384,400 kilometers away. Let's get back in our car, but this time, let's drive not around the Earth, but toward the moon. By the time we reach the moon, exactly 7 months would have passed since the start. We didn't go by car, but people did go there. Exactly 12 people have set foot on the moon to this day. Now let's expand our scale a little more. After the moon, let's imagine going to the sun. Again in the same car at the same speed of 100 kilometers per hour. By the time we reach the sun, exactly 177 years would have passed. The scale has grown a bit, hasn't it? But we are still very, very close in terms of the universe. We are within an incredibly narrow area. Let's go a little further. Let's get back in our car and head to Neptune. When do you think we would arrive? Pause the video and share your answer in the comments. If the comments have been posted, now it is time for the answer. It would take exactly 5,000 years to reach Neptune by car. We cannot travel that far, perhaps, but something we built has now exited the solar system. The Voyager 1 spacecraft, launched in 1977, managed to leave the solar system exactly 35 years later in 2012, and it is still on its way. It is currently exactly 22 billion kilometers away from us. If we could accelerate our car to the speed of light, it would take 1 day to reach Voyager. Now it is time to leave our neighborhood, the solar system. We want to leave, but where is the boundary of our solar system? Is it Neptune's orbit or Pluto's? According to some astrophysicists, is it the comet belt known as the Oort cloud? But the distance between these two is enormous. Even traveling at the speed of light, if we accept Neptune as the boundary, it would take 4 hours to exit the solar system. But if we accept the Oort cloud as the boundary, it would take 1.5 years to exit the solar system. Just changing the boundary creates a difference ranging from 4 hours to 1.5 years. And that's at the speed of light. We talked about what the speed of light means in previous videos. Let me put it this way. We can reach the moon at the speed of light in 2 seconds. Those are the kinds of speeds we are talking about. And we have not even left our solar system yet. On a comedic scale, we have not even moved 1 meter. And now, let's compare our solar system, which seems so enormous to us, with our galaxy and continue to challenge our minds. Let's try to travel to the nearest star, Proxima Centauri, approximately 4.2 light years away. Sounds close, doesn't it? Let's get in our car and try to go. Approximately 47 million years later, congratulations, you have arrived at Proxima Centauri. That is roughly equivalent to 2,500 human generations, or a lifetime multiplied many times over. Let's move a little further and go to the brightest star in the sky, Sirius, 8 light years away from us. We have now left our neighborhood, and there are star clusters. We cannot see all of them, but we can see some. For example, Betelgeuse is exactly 645 light years away from us. So how do we see this star from such a great distance? Because it is 1,000 times larger than our Sun. If we try to cross these star clusters from one end to the other, it would take approximately 1 million years using the Voyager spacecraft. We have now entered a different system, the radiosphere. We are talking about the area reachable by all the radio waves we have been broadcasting since World War II. This area is like a single blue grain of sand on a beach of sand representing the entire universe. Do not let the word grain mislead you. This area contains between 3,000 and 5,000 stars. We are talking about an area 200 light years in diameter. Let's leave this behind too and go even further, much further, to 1,000 light years away. That seems very far, doesn't it? No, we have not even reached 1% of the Milky Way galaxy. Just our own galaxy alone is an enormous mass containing approximately 400 billion stars. When we say billion, it sounds small to the ear, but if you try to count to 1 billion, it would take approximately 32 years. That is how large the number 1 billion is. Now try to imagine 400 billion stars. I wanted to convey that because things are about to get even more complex. If our galaxy has 400 billion stars and we consider that each star has its own planetary system, then we can speak of trillions of planets, and that is only within our galaxy. Our galaxy, the Milky Way, is 120,000 light years in diameter and 1,000 light years thick. Numbers are beginning to lose their meaning, and we are approaching incomprehensible scales. Let's set the numbers aside. Imagine our solar system is the size of a coin. The Milky Way galaxy would then be the size of the American continent. And remember, our Earth exists inside that coin, probably no larger than a dust particle on the coin. And on that dust particle exists humans, living beings, the oceans, the whales, all of it on that dust particle. Now it is time to shatter all perception, to break free from the distances and limits of our world. We have now left the Milky Way and are heading to our neighbor, the Andromeda Galaxy, 2.5 million light years away. Let's leave that behind as well. Let's go 110 million light years away. Before us is the Virgo supercluster, which contains us, Andromeda, and all the galaxies within it. This cluster holds thousands of galaxies. Let's not stop. Let's go even further. Before us will appear superclusters like the Virgo supercluster, each containing trillions of stars and thousands of galaxies. We have picked up speed. Let's go even further. We are now approaching what we call the cosmic microwave background radiation, the map left over from the Big Bang at the very first formation of the universe. When we arrived here, we have reached the end of the observable universe. At this moment, this is the furthest point that light can reach us from. And it is a vast system containing 2 trillion galaxies. I think you now understand the magnitude of these numbers. Is it over? No, of course not. The observable universe is 46 billion light years away. But what lies beyond? The truth is, we do not know. But when we calculate that the universe is expanding at an accelerating rate, we believe the actual universe must be 250 times larger than this. That means trillions of light years. That's it. So, what did this video teach us? After learning all these numbers and scales, what changed? That is of course a personal answer. But for the important figures throughout history, the answer to this question was the answer to everything they were searching for. Because the effort to understand oneself and the effort to understand the universe are in fact the same thing. That is why all the thinkers, philosophers and scientists throughout history searched for the answer to this question. The better we understand the universe, the better we understand ourselves. In other words, while we are trying to understand ourselves, ourselves, we are understanding the universe. The universe is not a phenomenon separate or different from us. Biologically, we resemble one another. Atomically, we resemble the universe. This video may have made us feel very small, but we are just as valuable as the universe itself. Knowing that every atom in our body was once gifted to us by a dying star tells us how meaningless all the troubles and wars within this world truly are, and at the same time, how limited the time we have truly is. Today, we took a small journey through the universe. Let's see what awaits us